We want to continue talking about orbital diagrams, but this time add some additional information of the energy. The box diagrams we were looking at previously just kind of had, total, all of the orbitals that were out there and just putting electrons into them. It's really common to instead arrange our orbitals spatially, like on the page, move the orbitals around with respect to the energy of those subshells. So you can see the idea. I have this energy axis going up. And so what that would imply is that the orbitals near the bottom here, like 1s, are the lowest energy, then 2s, 2p, 3s, 3p. And so actually this orientation, or this configuration, really clearly is showing the Aufbau ordering. And you can just kind of see the 1s is the lowest, that's why it gets filled first, then the 2s, that's why it gets filled, and you don't fill a higher energy subshell because it is literally higher up until you have to, right? Until those are fully occupied. We're still using arrows like we did with boxes to represent our electrons. Up arrows, down arrows, they pair up in a single orbital. Usually people use lines in this designation just because it's easier to draw a line than to write a full box. But it's still the same idea. Each line represents an orbital, and you will also note that entire subshells are written together, even when they are not. You include the empty orbitals. You include the entire subshell at a time. You can see in this these depictions that empty orbitals are included, those higher energy. That has more to do is because when you start to, that is not mandatory, but also isn't that rare to see because of implications of when you start to do chemistry with atoms, some of those extra orbitals might start to matter. But we're going to not worry too much about those. But for one things we can also look at when we're dealing with anything like this is we can ask questions like, what atoms are these? These are just depictions of electron configurations. And one of the ways we could do that is just counting. So, in this first one, I have 6. So that means this is carbon for being a neutral atom because it has 6 electrons. I moved up to 7, where that 7th is, Hund's rule. So this is nitrogen. And then I have 1, 2, 3, 4, 5, 6, 7, 8. So if I have 8, oxygen. And so we can see that these are just the atoms one after the other. You could have also, once you realized they went up one at a time, that it was just following along the periodic table. So let's see what that looks like. Let's draw orbital diagram for germanium, including my orbital energies. Just like with the box diagrams or electron configurations, we're always just going to be asking, what subshells do I need, right? Where are the electrons actually, going to be assigned? There is going to be the complication of what's the energetic ordering, but that comes from the Aufbau ordering. So the subshells are already written in the order from lowest to highest energy. And then you fill them in using that same Aufbau principle. So all of those still cook in, that idea of building up. So let's look to the periodic table. We can find germanium right there. That is squarely within the P block. We can see it is in the 4th period, so 4P, and then this is column 1, 2. So this is going to end with 4P2. So the highest energy subshell is 4P. It's going to end with 4P2, and we know that everything lower than that is full. Right, so the highest valence is the 4p2. Everything else is full. The 1s2, 2s, 2p, 3s, 3p, 4s, and 3d. You can look at the Aufbau ordering, and just everything below that has to be full. And the thing you just want to remember for what fullness means, s is 2, p's are 6, and yeah, there's a d type in this as well. That gets 10. We don't have any f's, but that would be 14. So let's draw the orbital diagram for germanium, including the orbital energies. It's always a good idea to start with that standard configuration to figure out kind of your baseline of where you're going. Draw your energy scale. We're starting at the bottom. We're going up. We know that 4p, again, has to be the highest. We can use that information from the periodic table. 4p has to be my highest energy. Everything else below that we can fill using Aufbau ordering, and we know it has to be filled up, right? This is the idea of building up. And so we draw lines for how many orbitals based on the type of subshell, S, P, or D, 1, 3, 5. We want to be careful. It's not we get kind of used to the number of electrons, right? Like S is 2, but really that's the number of electrons because there's 2 per orbital. P is 6 because you can put 2, 4, 6, right? Because you're putting 2 per. So when we fill it up, we do use those numbers. So again, those exponents on the standard notation, those are counting total electrons in the full orbitals. And because those aren't the 4p, we know they all have to be full. So this is the idea that comes from the Aufbau. We can visualize the Aufbau principle, that they are literally arranged vertically according to energy. You fill those bottom orbitals, work your way up. You know, the bottom electrons like provide support, or if you want to think about that's what the building up means. 4p then is where we actually have some, you know, kind of variation, or we have to decide where to put the electrons. We put our first one in. Hund's rule still applies for the second electron, so it goes into a different orbital and the spin points in a different direction. And voila, we have the orbital diagram for germanium with our orbital energies. It is a little more space intensive, but we have a lot of information there. This is one of the most complete descriptions of the electron configuration of an atom. It has a lot more information than just the standard notation over here. You know, we've got all this information about the orbitals, how they're filled, the spins of electrons are specified, and that's a really pretty image that we can generate. So one of the things we could ask ourselves is, who cares? You know, we have these electron configurations. We've done a lot of work to get into here. And so one of the applications we can look at is actually magnetism. And so electrons are the root of all magnetism. Magnetism comes from electron spins. And so these ideas of that you have up spins and down spins of electrons, that there's this sort of variability is what drives things that are magnets. So magnetic materials have more electrons with one type of spin. Either more all up or more all down, whatever it is can drive your magnet. And so other materials that are not magnets, how they respond to those magnets is based on the spins of those materials. And so you could have things that are diamagnetic or things that are paramagnetic. Diamagnetic materials are repelled by magnets, and paramagnetic are attracted to. So if you think of like a metal that you can pick up, say you have like a magnet and you can pick up, you know, like a paper clip or something, that means the paper clip is paramagnetic because it's attracted to the magnetic field. This image on the right, those golden cubes, those are very strong magnets. So those have a magnetic field. And then this object, that black square with a circle in it, this is what's called pyrolytic carbon. It's actually similar to charcoal, similar concept, but this is a very diamagnetic material. And so that means it is repelled by a magnetic field. And so we can see it is literally lifted up from the surface of the magnet. And so this idea of being lifted up is it's being repelled by that magnetic field. It is not attracted to the magnet. It is instead repelled by the magnet. And it's a strong enough repelling to push it up away in much the same way that, you know, a paperclip could be lifted up in the air to be attracted to a magnet. And so this idea of diamagnetism is really important. This underlies like magnetic levitation trains, those sorts of ideas where you have that you are using this idea of diamagnetism. And whether or not a material is diamagnetic or paramagnetic is understood based off its orbital diagram. It has to do with whether or not the electrons are paired or unpaired. So if we look at an atom like beryllium, 1s2, 2s2, all of its subshells are full. It has no unpaired electrons in a particular orbital. Beryllium is diamagnetic. If you had a beryllium atom and you put it in a magnetic field, it is repelled by that field. Paramagnetic materials have unpaired electrons. So when we look at the boron orbital diagram or the carbon orbital diagram, they have those unpaired electrons. What that therefore means is that those are going to be that those materials are going to be paramagnetic. They are going to be attracted to a magnetic field. Now, it's important to note, these descriptions are based off atoms. That piece of pyrolytic carbon on the last slide was a material, right? That's a lot of carbon atoms together in molecules. And so the properties of those materials are based on the electrons of the molecule. What orbitals are they in? What's the configuration? So it's going to be a little more complicated, but it's still the same idea. Having this depiction of where are the electrons, what orbitals are they in, what is the different spins, lets us understand things about what's going on, right? It lets us predict properties of those materials. And that's what we want to be able to do as chemists, make predictions based on starting at that atomic level, understanding and predicting the properties of materials.